Hi, it's Moser with a quick introduction to chemical bonding. After you've watched this video, you should be able to name the three types of chemical bonds and use differences in electronegativity to predict if atoms will form ionic or covalent bonds, as well as if those covalent bonds will be polar or nonpolar. You do need to already know what valence electrons are, as well as what electronegativity is. So, got a little random assemblage of objects here. Piece of white paper, remote control, a glass dish, a paper clip. Have you ever stayed up too late and stared at things and wondered, what is actually holding them together? Whoa! Like, how come they don't just fall apart? How come I can't just pull them apart easily? Well, I think you know that the answer is chemical bonds! And that's, of course, what we're here to talk about. So there are three major types of chemical bonds: ionic, covalent, and metallic. And we're going to briefly discuss all three and then focus on the first two. So in an ionic bond, atoms have actually traded electrons. One atom gives up valence electrons, one atom accepts those extra valence electrons, and then you have positive ions and negative ions which are strongly attracted to one another. And the force of that attraction, often between many individual ions, is what holds materials together. In covalent bonding, atoms are sharing valence electron pairs. So nobody has to give up anything. It's all sharing, folks. Metallic bonding is something that only happens between transition metals. So we're going to save that one for a little bit later. Let's recap. In ionic bonds, atoms have become ions, they've stopped being neutral, and now the force of negative and positive charges being attracted to one another is holding materials together. In covalent bonds, we have here the co-captains of the valence electron team. Atoms are sharing, just like co-captains share responsibility, atoms that are covalently bonded share their valence electrons. And then we have those silly metallic bonds that we only find in the transition metals. Here's a nice shiny piece of, I don't know, iron, tin, titanium. Any of those would bond metallically. But we'll talk about that later. So we're going to focus on ionic and covalent bonds for right now. And the first thing you should know is that there aren't a whole lot of bonds that are totally ionic or totally covalent. This is a continuum, a spectrum, if you will. And where any individual bond falls on that continuum really depends on how strongly each atom in the bond is able to attract electrons to it. In other words, it's electronegativity. So here we have random atom A and random atom B. And if we imagine that these things bond and they're sharing electrons, we're going to notice something here. That blue fuzziness, well, that's the electron cloud, and it sure looks like B is kind of hogging up the electron cloud blanket, so to speak. Well, what we would immediately know is that atom A is less electronegative. It's less able to pull the electron cloud towards it. And atom B is obviously, well, more electronegative. So it's able to more strongly attract the electron cloud. Okay, so in this case, atom B can't attract the electron cloud so strongly that it completely strips atom A of its extra electrons. They are still sharing, but the sharing's not equal. We should keep that in mind for later. You'll find some variation of this chart in a lot of places, and it describes this continuum pretty well. There's this one, there's this one. What they show are a couple things. First of all, that the maximum difference between any two atoms in electronegativity is 3.3, and the minimum difference possible, well, of course, it's 0. So what this comes down to is that if we took the atom with the greatest electronegativity of all, do you remember what that is? And the atom with the lowest electronegativity of all, that'd be fluorine and cesium respectively, and we wrote down their electronegativities and looked for the difference, well, we'd find that fluorine, with its electronegativity of 4, and cesium, with its electronegativity of 0.7, give us a difference of 0.3. So that's where this number comes from, this maximum. But you don't have to have the maximum difference in electronegativity to just decide that sharing isn't worth it and to go ahead and trade electrons. We consider anything from 1.7 difference in electronegativity all the way up to that maximum to be an ionic bond. Okay. So at 1.7 they give up the pretense of sharing. One atom grabs the electrons, the other one happily gives them up, and we call it ionic. Now, below 1.7, you're going to have to share, kids, because below a difference of 1.7, neither atom is willing enough to completely give up the electrons, nor is either atom able to attract them strongly enough to sort of steal them. So, atoms share, but not all sharing is equal. We said that from 1.7 to 3.3 we have a purely ionic bond. But anytime we have an electronegativity difference of 1.7 or less, the bond is covalent. So if we have a very small difference, say 0 to 0.3, very tiny difference, that would be this region on this chart. We call that a non-polar covalent bond. And if we have a slightly higher difference, from 0.3 to 1.7 difference in electronegativity, we call that a polar covalent bond. I kind of feel like we need to explore what those terms mean. Whoops, and I drew that circle in the wrong place. There we go. From 0.3 to 1.7 would be a polar covalent bond. So let's go back to our little imaginary atom A and atom B, who have bonded here and are sharing their electrons, but they sure aren't sharing them evenly. Atom B, as you can see, has sort of pulled most of the electron cloud over to surround it, leaving atom A kind of, well, with its poor little nucleus hanging out there in the cold. What this causes is a region of partial charge on either end. And when we think of polar covalent and charges on either end, a nice analogy is, well, it's under your feet, the Earth. So the Earth has got a north and south pole, and they have opposite magnetic charges, just like a magnet. Well, a polar covalent atom has got opposite charges as well. This area of partial negative charge here is because that blue fuzzy stuff that B has pulled over towards it, well, that's the electron cloud. And as long as that cloud is there, that's all electrons buzzing around, which have a negative charge. So that area of the molecule is going to have a partial negative charge. On the other hand, over here, where poor atom A's got its poor little naked nucleus hanging out in the wind, well, that nucleus is positive. So where the nucleus isn't surrounded by a bunch of electrons, that's going to be a region of partial positive charge. Well, what if we have two hydrogen atoms and they bond? Because actually, hydrogen atoms never exist on their own. They're always found paired with something else. And if it's pure hydrogen, it's paired to another hydrogen atom in a diatomic molecule. Well, what does it look like when they bond? Well, it looks like two atoms who have an exactly identical attraction to electrons. There are no poles. There's no region of partial charge. From end to end and top to bottom, this molecule is balanced. There's an equal concentration of electrons on each end, and nobody's nucleus is hanging out in the wind. This is a non-polar covalent bond. So again, non-polar covalent bonds create molecules with no areas of charge. Polar covalent molecules have areas of positive and negative charge on the ends, kind of like the Earth. Cool. So now, I think you're ready for a little bit of practice. Let's predict the types of bonds that will be formed by these pairs of atoms. To do this, you're going to need an electronegativity table. There's a nice one in Chapter 5 of your Holt Modern Chemistry, so you can grab that. I'm going to pull up an image of it. There it is. That's what we want. So let's look at our first couple here, lithium and fluorine. Well, lithium has an electronegativity of 1, while fluorine has an electronegativity of 4. That gives us an electronegativity difference of 3, which makes this a ionic bond, a very ionic bond at that. Well, let's look at magnesium and oxygen. So magnesium has an electronegativity of 1.2, while oxygen has an EN of 3.5. What's our difference? 2.3, which still puts us clearly into ionic territory. So now let's look at nitrogen and oxygen. We already looked up oxygen and know that it's 3.5. What's nitrogen? Ooh, 3. So this will give us our first covalent bond. And with an electronegativity difference of 0.5, it is polar covalent, but really just barely. Well, now let's look at hydrogen and carbon, something that we actually find bonded quite a bit. Oops, and I forgot to write my bond type. Let me take care of that. Okay, so now let's go back and look at hydrogen and carbon. We show an electronegativity of 2.1 for hydrogen and 2.5 for carbon, giving us a difference of 0.4. So 0.4, again, gives us polar covalent, but boy, just barely. What if we bonded oxygen to oxygen? What would the electronegativity difference be? Well, oxygen's 2.3 and oxygen's 2.3. That would give us a 0 EN difference. And that would give us a nonpolar covalent bond. So there you have it. Do you feel confident enough that you can identify the 3 major bond types, as well as use electronegativity differences to predict bond types, and describe the differences between polar and nonpolar substances? There'll be more on that later. Don't worry. Okay, keep going.